Hi, Physics 2, Mr. Janowski here. This is part 3 of the Chapter 37 slides. In the last part, we got more practice with Faraday's law and Lenz's law, and actually got to apply some math to them. And in this part, we're going to learn maybe the most important application of these ideas. So let's get started with that. So, what is the formula for magnetic flux? Maybe you've committed this to memory by now. Phi sub b, that's our symbol for magnetic flux, is equal to BA times cosine theta. So the strength of the magnetic field times the area times the cosine of the angle between the magnetic field and a line perpendicular to the area. So that's what this graphic is showing us. What is our formula for induced EMF? The induced EMF is equal to the opposite of N, which is the number of turns in our loop, times the delta phi sub b over delta t, times the rate of change of magnetic flux with respect to time. So what are some of the ways we discussed of changing the magnetic flux? So look at your formula for magnetic flux there, and you can either change. So we have phi sub b is equal to BA cosine theta. Well, if you want to change phi sub b, you can either change B, change the magnetic field, change A, change the area, or change theta, which is the angle between the magnetic field and the area, or really the line perpendicular to the area. So think back to last year in Physics 1. What is that the symbol for? That funny looking thing that looks like a W, but really it's not a W. That is lowercase omega. And omega is the symbol for angular velocity. So we learned kinematics for rotational motion, things like that. But basically, if omega is constant and theta is 0, at t equals 0, then we can just use this simplified version of this formula, saying theta is equal to omega t. And now a calculus question. What is the derivative of cosine omega t with respect to t? So I'll give you a second to think about that. So yeah, d dt of cosine omega t is going to be negative omega sine omega t. So yeah, that idea is going to come up. So last chapter we learned about electric motors. So I made these graphics, these little drawings. They're really a pain to make. But yeah, basically the idea is you have a magnetic field and you have a loop going through it. And if you put a current through that loop of wire, you can create a torque that's going to turn that wire. And so, yeah, getting something to turn is very useful. So if you have an electric motor, you're going to be turning electrical energy or electric potential energy into mechanical energy. So that's what a motor does. So instead of having the stationary wire and then putting a current through it and getting it to turn, what would happen if you weren't putting a current through this loop and instead you started turning the wire? So instead of passing a current through the loop, we somehow cause the loop to rotate with a constant angular velocity omega. So we somehow cause it to rotate. So what's going to happen in this case? We'd be changing the angle, and by changing the angle, we would be changing the flux, and this would induce an EMF. So look at this middle formula over here. Phi sub b is equal to BA cosine theta. Well, we're not changing B or A, but we are changing the angle. And if phi sub b, if your magnetic flux is changing with respect to time, you're going to be inducing an EMF, an electromotive force, basically a voltage. So yeah, here, deriving this idea. So this is the formula we've been using. Epsilon, EMF, is equal to minus n times delta phi sub b over delta t. Well, yeah, the big boy version of that, instead of delta, these things, it's really the derivative. So EMF is equal to negative n d dt phi sub b. And if phi sub b is equal to BA cosine theta, and theta is equal to omega t, well, look what happens here. Blah, blah, blah. And this is why I asked you for what is the derivative with respect to time of cosine omega t. You bring out this omega here, and the derivative of cosine is going to be negative sine. Well, the negative of that one cancels with the negative that was already there, so you end up with this expression. Epsilon is equal to NBA omega sine omega t. So this is the formula for the EMF produced by an AC generator. So yeah, this is important. This is how a generator works. So here's our formula. What do all these symbols mean? Epsilon is EMF, voltage basically. N is the number of turns. So this is just a number. This is dimensionless. B is our magnetic field, which comes in units of Teslas. A is the area, which it's an area. It's got to be in meters squared. Omega is the angular velocity in radians per second. So rads per second. We like radians for this, not degrees. And t is time in seconds. So I've been calling it angular velocity. In this context, we would probably rather call it angular frequency instead of angular velocity. So this is angular frequency, different than regular frequency. So omega is angular frequency. I should have changed that from angular velocity to angular frequency in units of radians per second. So how does omega relate to frequency f? So omega is equal to 2 pi f. And f is going to be cycles per second, or inverse seconds, or hertz. That's what a hertz is. So this is the relationship between angular frequency and regular frequency. So if you say the current in the U.S. Or the voltage in the U.S. oscillates at 60 hertz, 60 hertz is the F. That's this. If you wanted to turn it into its angular frequency, you would have to run it through this. So 2 pi times 60. So if we were to sub in 2 pi f for omega, because omega is equal to 2 pi f, into this expression here, we're going to get a new version of the generator equation. So sometimes you would have your frequency in terms of its angular frequency omega. Sometimes you would have it in terms of its regular frequency f. So this equation might be more useful. But same thing, just different versions of what the frequency is. So if we're looking at this, let's see, we have epsilon is equal to NBA omega sine omega t. These formulas are getting to be a mouthful. So I'm starting this off with the coil this way. So at time t equals 0, we're just going to start the clock right now. The angle theta between the area, remember this is the perpendicular to the area, is A, and the magnetic field B, well, this angle is 0. So at this time, epsilon is equal to NBA omega sine 0 is our angle. Sine of 0 is 0, so that means there's no EMF. We would have 0 volts. Now try to imagine what's going to happen as this thing starts to rotate counterclockwise like this. We are suddenly going to start to have an EMF. So we're going to have a current, EMF will be induced, which means we're going to have a current flowing through this thing. So try to figure out, using Lenz's law and the right-hand grip rule, which way is the current going to flow? Is the current going to flow from here along this bottom one and then go A to B to C to D and then back out through the top one? Or will the opposite happen? Will it come in through the top one, go D to C to B to A, and up to this one? So look at that, think of what's going on, and in 3, 2, 1, I'm going to give you the answer. So 3, 2, 1. The answer is, it's going to go from A to B to C to D. So if we go back to this picture, currently we have flux going to the right through this loop, and we're actually at the maximum amount of flux we're going to get. So a short time later, as the thing starts to rotate or continues to rotate counterclockwise, we're going to be losing flux to the right, which means, according to Lenz's law, the induced current has to be creating more flux to the right to make up for the flux that we're losing. So using Ampere's right-hand grip rule, hopefully you can see that the current would need to flow this way. So yeah, we're going to have the current flowing that way. So just kind of the beauty of math. Yeah, there's this huge connection between rotation and sines and cosines. So yeah, unit circle and all that stuff. But basically what's going on here is the fact that we have a constant angular frequency of omega. The fact that this thing is going to turn around at a constant rate with a constant angular frequency or angular velocity is going to give us a sinusoidally varying voltage. So look at this top expression here for phi sub b, BA cosine times omega t. So at t equals 0, we would have the maximum amount of flux that we're going to have. So it would be the green line here. And as it starts to turn, we're going to be losing flux, and then we're going to have flux going the other way, and then we're going to be back to 0, and just like this. And as this happens, we're going to have an induced EMF, and that one's going to vary sinusoidally. So we're going to go from having 0 volts to our maximum positive voltage, then back to 0, and then our maximum negative voltage, and then back to 0. And it's just going to keep varying like this. So, yeah, comparing this thing we just learned, a generator, to a motor. So last chapter we learned motors. In a motor, the input is electrical energy or electrical potential energy, and the output is mechanical energy. So what does a motor do? It turns electrical energy into mechanical energy. A generator is the flip of that. A generator is going to turn mechanical energy into electrical energy. So where are we going to get the mechanical energy for our generator? We need something, could be lots of things, to turn a turbine connected to the shaft of the generator. So this isn't absolutely the only way to make energy, but this is kind of the classic way. This is the way it's usually done to make electrical energy, I should say. Yeah, we need something that's going to turn a turbine, and the turbine is connected to the shaft in our generator. And that's going to turn this thing, this metal loop with many turns, with N turns, in a magnetic field, and this is going to induce an EMF. That's what a generator does. So yeah, the something that's going to do this, that's going to cause this thing to turn, it varies. There's lots of ways to do it. So if you have hydroelectric power, what ultimately you're going to do is you're going to have high water up here. It's going to flow down low and gain kinetic energy. It's going to turn GPE into kinetic energy in the water, and that's going to turn the turbine, and that's going to turn here in the generator, and ultimately that's going to give you electrical potential energy. You might also have wind power, which is just going to turn kinetic energy of the air, you've got moving air, into kinetic energy of the turbine and then electrical potential energy. Now, unfortunately, we usually do this through fossil fuels. This is where the majority of energy in the United States comes from. So how's that going to work? It's going to start at a different place. You're going to be turning chemical potential energy in the coal or the natural gas or whatever kind of petroleum thing you're burning. You're turning chemical potential energy into heat, and that heat will heat up water. It'll boil water, turn it into steam, which has kinetic energy, and the steam is what actually turns the turbine, and that gives you electrical potential energy. You might also be doing this with nuclear energy, which is much greener than doing it with fossil fuels. Perhaps not ideal still, but it's basically the same thing, only where you're getting your heat from. Instead of burning fossil fuels, you're taking nuclear potential energy. You're doing E equals mc squared, basically. And that's generating the heat. And that heat is making the steam, and that steam's turning the turbine. And that turning of the turbine, this is the mechanical energy that is ultimately converted into electric potential energy. So, to review, what is the formula for magnetic flux? Phi sub b is equal to BA cosine theta. What's the formula for induced EMF? So it's this one. It is, really minus n times the derivative of phi sub b with respect to t. And what is the generator formula? So this is the one we learned today. So epsilon is equal to NBA, the area, times omega times sine omega t, where omega is the angular frequency or angular velocity, really the same thing. So, what are the input and output of an electric motor? In a motor, your input is electrical energy and your output is mechanical energy. So, what are the input and output of an electric generator? It's the opposite. A generator is going to turn mechanical energy into electrical energy. So a motor does the opposite. In a motor, you're turning electrical energy into mechanical energy. In a generator, you're turning mechanical energy into electrical energy. So that's it for part 3. Hopefully you found that interesting.